and then the dust which has stuck to this one will be analyzed in the lab. And we were discussing here outside the house about this. The spacecraft here is protected by some kind of whipple shields or bumpers here in order to survive this flyby. And these bumpers, they are several foils behind each other, and they are designed in such a way that the particle up to the size of 1 centimeter diameter can hit this at 6 kilometers per second and does not destroy go through these bumpers. So when it hits the first bumper, then it creates a shock wave, ionizes, goes through this first one, spreads out, and then gets caught by some of these later layers in this structure. So it's some kind of active armor, and that was really needed. The spacecraft here is a more detailed view of it. There was a couple of instruments. So one, the main mission goal is to collect 500 microparticles out from this flyby by the comet. And then in 2 different phases of this we have collected on this one. One is when we fly backwards and then collect interstellar dust, and one is when we fly forward here and collect this cometary dust. And all of these will then be analyzed on ground. The flyby by the comet is at 6 kilometers per second, or was at 6 kilometers per second last the 2nd of January, and then this dust collection that is at much higher speed, so something 40 kilometers per second, and then flying then backwards, looking at this more. Here is a number of instruments on these front panels where we analyze, then look at the rattle when these particles hit, so we can get an estimate of number of particles. Then there's a camera system looking at the comet, and then we have this time of flight mass spectrometer here, which I will describe very briefly and show. The aerogel is a silicon compound looking like this at very low density, and this is this cushion is made by a grade, so varying density aerogel, so that it has a very, very low density at the surface, and then it gets stiffer and stiffer when it gets lower in order to try to collect these particles properly. And this is what it looks like when you...
Is that a true picture or a composite picture?
Pardon?
Was that a true picture or a composite picture? Because it's so hydrophilic that you don't want to hold it, you don't want to squeeze the woman into vacuum, so...
No. Actually, you can touch it. I have a piece of this aerogel, so you can keep it in your hand, and it feels just nasty. It's not a very nice feeling.
Oh, that's why she has no nails.
No, it's...
No. I mean, you can have it.
It's absolutely no problem. So
it's mainly if it's an unclean shape, then you also have some of the sharp SiO2
But isn't it
crystals.
hydrophilic, so it soaks out the water of the
it's an ordinary solid, so I would say that it does not feel very strange actually. There is depends very much on the density. So if you have a soft one thing, then it's a little bit like rubber or something like that feeling, and then when you have a very stiff one, then it's like sandstone or something like that. But that is something.
It has that friction feel.
Yeah, so it's like a piece of chalk, and you get something nasty on your fingers, and it's not fun. But here is then a schematic on when we collect these particles. So they hit them here. They have shot different kind of particles, and they go into these trenches into this one, and you can see that there is always this kind of explosive things, so they fragment and they go into different places. So it will be a real challenge to dig these out. And then the cavities here, if you have a 1 micrometer particle coming in, that's a relatively large one, then you can see that we have a 1 micrometer size big hole going into this thing, so it's a challenge to find them from this half parameter size thing. But that will be a future problem. The Silen thing now works in such a way, there is a small cavity goes in here. The reason I show it quite in detail here is a silver plate, and the particles come in here, they have to go past this obstacle somehow to hit this silver plate, and are getting ionized here and then fly into the instrument here. This geometry seems to be important to understand here because of reasons I will counter. So the function of the instrument is really that we get these dust grains somehow onto a silver plate. When they collide here, they create a plasma, completely ionized, and here's a post-acceleration grid at 1 kilovolts. So we rip these ions off, let them fly through a reflectron here, and collect them at the detector. And this flight time here is a direct measurement of the mass on the particles. There is some leakage in this, so some neutrals, there may be some chemical processes here or neutralization, so some neutrals may hit this backplate and then cause secondary electrons or whatever particles to hit this, and that can do some harm to the adaptation. Here's an image of this instrument. It's the size of a bazooka roughly, and the elements are here. This is a lab spectrum, typical that we have recorded in Heidelberg with the Van de Graaff accelerator used as the dust accelerator, where we can get up to, this is typically something maybe 14 kilometers per second, and only conducting particles can be accelerated. Yes?
So the particles didn't have a short-term mass, but why did you assume that the radius of the terminal was the same?
Yeah, the trajectory, this reflectron is done in order to reduce some of this velocity dispersion. Because when it splashes towards this, you get an energy distribution in this plasma cloud. And that you want to remove. And that Mamurian showed sometimes that you can do by doing this kind of tricky electric field, so you get this trajectory. So effectively a slow particle does not penetrate so deep into this device, and a fast particle penetrates deeper and gets more flight time that way. So it compensates so everyone gets to the detector at the same time. So it simply improves this mass resolution. That's what it is for. And the operation is such now that this point here, that is the band when it hits this plate. So time starts from this point. And then we have a square root dependence here, and all this mass line comes out. This is hydrogen, then we have carbon and all this. And this is then translated here into a mass spectrum, so simple formula just digging this out. And we have some kind of calibration injection here, so we can get also this amplitude scale properly out from this thing. And our surprise was huge. This is the reason I wanted here to give this talk. When we were sitting in the, looking into the interstellar dust entrance to the solar system, so looking into the direction, we know that dust is coming. Then we got a handful, so we got about 40, actually 42 dust events. So some of them negative, because we can switch the polarity of the instrument, and some of them positive. And the second event we got looked like this. So we have a huge impact here. This is a semi-logarithmic scale, so it's really a very large one. And the distance between this edge and then the actual spectrum here is very long. And you can see that we have some kind of very well-resolved thing. So there's structure here, and there is structure here, there is structure even at the very edge of this spectrum. And here is then the resolved, so it's translated into this mass spectrum. Here we have mass 109, so here we would have the silver lines, which usually we see if we have some kind of inorganic compound in. And we have been trying to explain that, hey, we have some instrumental effect or something like that, but that does not apply. So we have not been able to verify for ourselves, even dreaming about explaining this as some kind of failure of the instrument. So all checks we have done is really that it seems to be solid. And if it is really solid, then we have to accept this fact that we have a semi-saturation, we have a mass resolution of about, so delta m per m is about 250 here, which means that if we have a very dense forest of peaks, then it starts to saturate at this point, and only very well-separated peaks will show up on this other bulk. And these masses go up, I have plotted them up to about 1,000 here. So we have something which is a really kind of polymers and heavy thing. This was the first spectrum we got. And here we have the unfortunate thing that the impact time happened to come just a little bit before here, because we had designed the instrument in such a way that we tried to get somewhere in the middle this one, but we never anticipated to get this huge masses into the instrument. And this is also a case now where we can see, one can argue then a little bit about how shifting this, but looking at the difference between different mass lines, one can get some kind of sense out of it. And this we have then started to look at what kind of fragments will we get out, what kind of triplets or molecular fragments, and then come to some kind of conclusion or thoughts that it seems to be some kind of nitrogen things in this quasi three-dimensional thing where these molecules snap, and then we see these kind of fragments in this spectrum. So that was what I wanted to say, and the conclusion is really that for the cometary flyby also, 100% have a single of these 29 flyby spectra that would show some kind of inorganic signature. They all can be interpreted as some kind of carbon or organic-like stuff. So this is then something which is in contradiction to these Halley measurements that one definitely will see. And then finally, on the Rosetta spacecraft, there is also something else flying. There's a TOP-SIMS instrument which is schematically shown here, and then a picture of this instrument, 36 kilograms instrument flying with this one, and that will be operated in such a way that we collect at low speed when we circulate and follow this comet for half a year, collect on a substrate plate, I'll get it back. On a substrate plate here we create or collect our dust samples. Then we can put them into a chemical station where we can heat them or get some kind of water on them, so we can do some kind of water-based processing. We have a microscope in it, so we can make an image here of these. So we have about 1,000 ccd here, which we can then image in roughly 1-to-1 these. Then we can put them into a measurement station where we shoot by an iron gun on top of this one. This target plate can then be moved by 3 micrometers across, and the beam size width is 50 micrometers. So we can make a TOP-SIMS then with a lateral resolution of 50 micrometers or some kind of final solution by squeezing it around. And then we have a mass resolution of this actual measurement thing here about 2,500, so we should be able, for instance, to distinguish between CH and C13, so we should be able to do isotopic measurements. And this instrument will now be commissioned the 3rd of September, so it's pretty interesting now to see how we hope it will get to go. So, thank you.
That's time for lunch.
That's a good question. So there's a group in Vienna who's doing the chemometrical studies and trying to find something or doing it. And we are starting a laboratory program to set up a similar or this a copy of this instrument in a lab in Lindau to start to collect spectra. And these spectra will then be compared to other TOP-SIMS instruments, and this interpretation is a hard thing, yes. So that's all I can say at this stage.
Did you say that you have water processing on the Rosetta spacecraft? Do you take water with them?
No, yeah, there is some compounds that when we heat them, we can generate some. So some of these targets have crystal water in these. So we have to heat them in order to get this water into action.
You heat the collected material? Or
Yeah, we can heat the collected material.
last question.
How representative these particles would be of the whole dust cloud when you are collecting them through such a tiny opening?
The dust feeds around 300 meters per second, 2 to 300 meters per second, moving roughly at thermal speeds, and we have 72 substrate collection plates, so we will put different plates at different times, and then we put them in storage, and then we will be able to measure for about 2,000 hours.
Okay, thank you. And, next is Torstein.